OJ-287, Extreme Black Hole Systems, Secrets Revealed. The Extreme Black Hole System OJ-287 has just become even more intriguing. Join the adventure of the cosmos with Dr. Ethan Siegel as he explores some of the universe's most profound mysteries. In the vast expanse of the universe, black holes are abundant. When black holes collide, a substantial amount of their mass is transformed into energy, manifesting as gravitational waves during a momentary burst. Over an extended duration, these black holes orbit each other with cycles ranging from 1 to 10 years. And pulsar timing can detect the accumulative effects caused by these pairs throughout the universe. Different detectors are needed to capture the gravitational waves generated by various mass sources. Most of these black holes are relatively small, typically just a few solar masses. When the two arms of an optical interferometer are perfectly equal in length and a gravitational wave is absent, the resulting signal appears null, maintaining a steady interference pattern. However, when the lengths of the arms adjust, a genuine oscillating signal emerges, altering the interference pattern over time in a predictable manner. This method is essential for directly detecting the presence of gravitational waves. Nevertheless, massive, supermassive black holes, which can weigh millions or even billions of solar masses, reside inside galaxies. There are three primary methodologies for detecting gravitational waves: ground-based laser interferometers, space-based laser interferometers, and pulsar timing arrays. Each method is attuned to different types of gravitational wave signals. While LIGO was the first initiative to pick up gravitational waves at high frequencies, the nanograv collaboration has recently found compelling evidence at much lower nanohertz frequencies. Pulsar timing has emerged as one of the foremost ways to explore the longest wavelength gravitational waves, which are chiefly generated by the heaviest orbiting pairs of supermassive black holes. In fact, black holes that are too massive for LIGO to detect necessitate longer baseline gravitational wave observatories. The accompanying image illustrates three future spacecraft, known as LISA, or Laser Interferometer Space Antennae, which will operate in a trailing orbit behind the Earth. LISA is poised to be our first space-based gravitational wave detector, capable of identifying objects thousands of times more massive than those detectable by LIGO. Arranging a network of LISA detectors at various points in Earth's orbit would facilitate the detection of even merging supermassive black holes, a concept referred to as the Big Bang Observer. LISA, along with the Big Bang Observer proposal and pulsar timing arrays, could potentially observe these phenomena directly. The illustration also conveys how numerous pulsars monitored within a timing array could register a gravitational wave signal, as space-time is disturbed by these waves. The longest wavelength gravitational waves, like those produced by the most massive pairs of merging black holes, can only be detected through techniques that utilize extremely long baselines, such as pulsar timing arrays. Likewise, a sufficiently sophisticated laser array may, in theory, given sufficient time, these black holes will eventually merge, with the final stages of this merger driven by the emission of gravitational waves until their event horizons make contact, culminating in a merger and ringdown. The most massive known binary supermassive black hole is OJ-287, first noted in 1887, acknowledged as the largest pair of black holes in the universe. The gravitational waves from OJ-287 will produce such long wavelengths that they will be beyond LISA's detection capabilities. A longer baseline gravitational wave observatory could spot it, as might an advanced pulsar timing array. Although OJ-287 was initially imaged in 1887, it wasn't until the 1960s that its properties and distance were accurately determined. Situated approximately 4 billion light-years from Earth, This system consists of black holes weighing 150 million and around 18 billion solar masses as they orbit each other. The accompanying diagram illustrates the sizes of the event horizons of these two supermassive black holes within the OJ-287 system. The larger black hole, at around 18 billion solar masses, has an event horizon the size of 12 times Neptune's orbit, while the smaller black hole, clocking in at 150 million solar masses, compares to the size of Ceres's orbit around the Sun. Remarkably, the heaviest known black hole is only slightly larger than OJ-287's primary black hole. Every 11 to 12 years, these black holes complete a full orbit. The double peaks observed in the flares emitted from OJ-287 correspond to the smaller black hole traversing the larger black hole's accretion disk twice during its orbit. The frequency of the flares, alongside the time-based variations in their orientation, can be accurately predicted using Einstein's general relativity. Due to the effects of general relativity, their orbits precess significantly, at an angle of 39 degrees per revolution. The accompanying animation portrays a lower mass black hole moving through the accretion disk surrounding a more massive black hole. Each time the smaller black hole breaches the disk, it triggers a flare. Given enough time, it's expected that these black holes will gradually draw closer and eventually merge, emitting a remarkable gravitational wave signal in the process. This repetitive double flare phenomenon is a notable feature of OJ-287. The flaring bursts occur as the lighter black hole breaches the accretion disk of the heavier black hole. A close-up and a broader view of the central nucleus of the nearby galaxy NGC 7727, just 89 million light-years away, showcase the nearest known pair of binary supermassive black holes, which are separated by 1,600 light-years. While environmental interactions can prompt supermassive black holes to approach one another, the ultimate phases of their inspiral and merger are expected to result primarily from gravitational wave emissions. Binary supermassive black holes appear to be relatively common at the cores of galaxies, accounting for approximately 1 in 1,000 galactic systems. This double quasar isn't a solitary case and represents around 0.1% of all quasars found. When two supermassive black holes orbit each other, they not only disturb and accelerate surrounding matter, but also create definitive signatures in the emitted electromagnetic radiation. This radiation complements that emitted as gravitational waves, opening another pathway to directly detect them and providing a means to independently verify the masses of the black holes. While the radio data shown here pertains to the binary black hole system 3C344, the underlying physics closely parallels that of OJ-287. The space-based radioastron telescope, working alongside ground-based telescopes, in VLBI, radio signals from each telescope are captured before being transmitted to a central location for analysis. Each data recording is stamped with the precise time from an extremely accurate atomic clock, which aids scientists in syncing observations accurately. As the distance between the telescopes increases, so does the potential resolution of the observations. This approach allows for our most detailed observations to date. An X-ray and radio composite of OJ-287 captured during one of its active flaring periods illustrates the orbital trail indicating the motion of the secondary black hole. This binary system comprises one supermassive black hole weighing approximately 18 billion solar masses and another weighing about 150 million solar masses. Upon merging, these black holes may release an astonishing amount of energy in the form of gravitational waves, equivalent to what is produced in the most energetically injected galaxy cluster. Recently, a long ribbon-like radio jet was discovered, enhancing our understanding of OJ-287. This groundbreaking observation, made with the radioastron telescope paired with a 27-element ground-based array, achieves approximately 15 micro-arcsecond resolution for the distant OJ-287 binary system. The ribbon-like jet reveals temperatures exceeding 10 trillion Kelvin, with the shape suggesting the presence of potent magnetic fields near the more massive of the orbiting black holes. In just about 10,000 years, these black holes are anticipated to merge. The accompanying illustration delineates the various stages involved in a supermassive black hole merger and the expected gravitational wave signals that scientists predict will emerge throughout the event. Once the two black holes approach the same event horizon, no further gravitational waves will be emitted except for the ring-down phase caused by the alteration in the shape of the post-merger event horizon. The merger is projected to release an astounding 3 times 10 to the 54th joules of gravitational wave energy, marking an inevitable event that could break existing records. Discover the hidden mystery, OJ-287's unusual plasma jet. Imagine a galaxy that has captivated astronomers for over a century and a half, located a staggering 5 billion light-years away. This galaxy, known as OJ-287, has sparked intrigue and debate among scientists due to its fluctuating brightness, which hints at the presence of 2 supermassive black holes merging at its core. But here's where it gets truly fascinating. A recent breakthrough by an international team of researchers, led by Dr. X. Evelia Traianu from Heidelberg University, has resulted in a detailed image of this enigmatic galaxy's heart. Utilizing a space radio telescope, the team captured an unprecedented image that reveals a previously unknown, intricately curved segment of the plasma jet emanating from the galaxy's center. This discovery sheds light on the extreme conditions surrounding supermassive black holes, which are known to be the driving forces behind the active galactic cores, or blazars, like OJ-287. These black holes consume matter from their environment and can expel it in the form of colossal plasma jets, which consist of cosmic radiation, intense heat, heavy atoms, and magnetic fields. Dr. Traianu, a postdoctoral researcher working with Dr. Roman Gold at the Interdisciplinary Center for Scientific Computing at Heidelberg University, emphasizes the significance of this new image, stating, "We have never before observed the structure in the OJ-287 galaxy at the level of detail seen in the new image. The newly captured image penetrates deep into the galaxy's core, revealing a ribbon-like structure of the jet that is sharply curved. This observation not only enhances our understanding of the plasma jet's composition, but also its behavior. Some areas within this jet reach astonishing temperatures exceeding 10 trillion degrees Kelvin, indicating the release of extreme energy and movement in close proximity to the black hole. Additionally, the researchers noted the formation, propagation, and collision of a new shock wave along the jet, which they attribute to an energy measurement in the trillion electron-volt range, linked to an unusual gamma-ray observation made in 2017. The groundbreaking image was produced using a sophisticated ground-space radio interferometer, which combined a radio telescope in Earth's orbit, a 10-meter-long antenna from the Radio Astron mission aboard the Spectre-R satellite, with a network of 27 ground-based observatories scattered across the globe. This innovative approach allowed the researchers to create a virtual space telescope with a diameter 5 times that of Earth, achieving high resolution due to the vast distances between the individual radio observatories. The imaging technique employed takes advantage of the wave nature of light, utilizing overlapping waves to gather data. The findings from this interferometric image bolster the hypothesis that a binary supermassive black hole resides within the OJ-287 galaxy. Furthermore, it provides crucial insights into how the movements of these black holes affect the shape and orientation of the plasma jets they emit. Dr. Traianu notes, its special properties make the galaxy an ideal candidate for further research into merging black holes and the associated gravitational waves. As we delve deeper into the mysteries of OJ-287, one can't help but wonder, what other secrets lie hidden in the cosmos? Are we on the brink of uncovering more about the nature of black holes and their impact on the universe? Join the conversation and share your thoughts. Do you believe we are close to understanding these cosmic giants, or is there still much more to discover?